Hey guys, Alex from cnc-o-rama here to talk to you today about can cycles. Now, when you think about can cycles, you're probably thinking about something like soup made of bicycles that's been canned. Can we start over? All right, so we're talking about can cycles. So you see group 9 right here. These are our can cycles. This is definitely not all the can cycles. There's a bunch more. Um, But these are the most common ones that I use and most people use, I think. So we'll go over, I'll mention some of the other ones while we're doing this, but we're going to start with these. And then this is the part I want to program. So I have 30 drilled and tapped holes. So we're going to put the origin here at the corner. So it's a 1/2 inch in X and Y to this first hole, and then it's a 1/2 inch grid pattern to all these other holes. So as far as the location of those holes, that's pretty straightforward. So the first thing we're going to do is spot drill. So let me just go back to NC Viewer and start typing out some code for this. So I'm not going to type the complete code, but maybe we should start by doing a tool change to a spot drill. So we can do M6 is tool change, and then maybe let's just call the spot drill tool 1. That'll do our tool change. And then we probably want to turn the spindle on, so we can do like M3, and I'm just going to give it kind of a generic number. I'll just say M3S 5000. And that spindle speed is really going to depend on our tool and the workpiece material that we're working with. We have our tool. We did our turn the spindle on, and now we need to we should probably wrap it to that first point. So that's going to be x 0.5, y negative 0.5. So we can do a g0, x 0.5, y negative 0.5. And then from there, we probably want to come down near the part in z. So on our first z move, and we can look back at this. I'm not sure if we talked about G43 in the last video. Tool length compensation. So this is where you're activating your tool length, so the machine knows where your tool tip is. And this should always be done on your first Z move after the tool change. So G43 Z. I'm just going to say Z1. Let's assume the top of the part is Z0 here. And then this is still a rapid move because G0 is active. G43, sorry, I also forgot H1. So the G43 and H1 tell it to activate the tool height for tool 1 in the tool table. Okay, so now we are at Z 1 inch above the part. So we can do our G81. Okay, it's G81. So on our G81, I'll type this out first and then we'll look at exactly what's happening. So x 0.5, y negative 0.5. And these numbers are redundant here because we're already at that location. But it doesn't hurt to be redundant on something like that. And then we need a z. Okay, so ultimately we're trying to make quarter 20 tapped holes. And so we're going to spot drill, and then we're going to drill with, this is a number 7 drill, 0.201, and then a quarter 20 tap. So we know the nominal major diameter of a quarter 20 tap is a quarter inch. Maybe we want to chamfer that front edge of the hole a little bit. So we want to actually go deep enough. Maybe we should make a 0.3 diameter chamfer when we do our spot drill. So this is kind of the way of thinking of that. So let's assume we're using a 1/2 inch spot drill. It's 90 degrees. And not all spot drills are 90 degrees. Sometimes they're 82. But for this one, we're using a 90, let's assume. Okay, so and then if I broke this up into 2 right triangles on the tip. So if you look at just half this diameter, this is the radius. This should be 0.25 from here to here. And that's actually equal to the tip length, 0.25. So if you kind of think of this as these 2 right triangles, you have a tip length of 0.25 on a 1/2 inch 90-degree spot drill. Okay, so now we're talking about our Z depth. So it's again, we're assuming the top of our part is Z0, and we want to leave a 0.3 diameter chamfer on this hole, so that when we drill and tap, there's still like a nice edge at the top of that tapped hole. So if we're assuming a 1/2 inch spot drill has a 1/4 inch tip length, that means the tip is basically half the diameter of however deep you're going. So if we want to go and leave a 0.3 diameter, then the tip length or the depth in that case would be half of that, 0.15. So I'm going to go Z negative 0.15. And then I need an R. So the R is, you can think of that as the retract. So for now, I'm just going to put, I'll put 0.25. Okay, and then it's always good to put a feed rate. Really, you should put a feed rate. I'm going to say 15 just for this. Okay, so that's our code for spot drilling that first hole. So now all we have to do is list the XY points of all of the rest of these holes. So maybe we'll go down first, so we can do, and I'm going to do another thing that's redundant here. I'm going to put in an x.5, which we actually don't need. So we can say y negative 1, x.5, y negative 1.5. So that's going to give me these next 2 points. This is y negative 1, y negative 1.5. And then we can move over to this one. This is x 1 inch. And that's still y negative 1.5. Again, I can leave, since we're already at y negative 1.5, I don't need to list that second y, but I'm just doing it so it's a little easier to read. Okay, and then we're, now let's go up. So we can go up to here. So probably an easier way to do this would have been to go all the way along x and then come down and all the way along x this way and then do it this way. Okay, so our next point, x1, y negative 1. And keep in mind, I'm putting a decimal on every whole number. That's super important. Some machines assume if there's no decimal that you're talking about 10,000ths of an inch. So y negative 1, it might interpret that as y negative 0.0001. So that decimal is super important. Okay, so I'm going to stop there. Obviously, we have 30 holes, and there's a path. I mean, we get the idea. You just have to list all the x, y values, and then to cancel our can cycle, we need a G80. So we can, now that we have some of the code, let's actually plot this. Is that right? So x.5, y negative 1. And let me orient this so we can. I went there. Oh, I have the same point twice. And that's another reason to use some kind of simulator. So we started here, moved to here, moved to here, moved to here, moved to here, there. And NC Viewer doesn't do a good job of simulating the exact motion because it's just showing going down to that negative z and then it just comes straight across. So the drill is actually going to go down, come up, wrap it in the next hole, come down, come up, wrap it in the next hole. So it is going to retract between each of those holes. But what this does do is exactly catch the mistake I just made of showing just where those holes are. Okay, so let's look at this now. So with G81, as we just saw, we have an X, a Y, a Z, an R, and an F. So let's look at what those numbers and letters mean in a little more detail. So every time a G81 is called, it's going to do these 4 steps in a row. So it's going to first wrap it to the XY location. So let's look at that. When we called our G81, we were actually already at that XY location. So it didn't have to wrap it anywhere, but it still does that step. Even though we were there, it takes that into consideration. Okay, then rapid to R plane. So this is an absolute Z value. So we already have a Z, so we couldn't have a second Z in this. But R is actually a Z value. So rapid to R plane. So let's look at what that means. So R plane is 0.25. So if you imagine a plane a quarter inch above the part, that's what that is. So we were at Z1 here, and then we're going to rapid to Z.25. Okay, now we're going to feed to the Z depth. So let's see, what is that Z depth? Is negative 0.15. So from that R.25 or the Z.25, we're going to feed at 15 inches per minute down to Z negative 0.15. And next we're going to rapid back out. But this is important. There's a catch. G98 or G99. Which one's active? In most cases, when you turn on the machine, G98 is going to be active. So let's look at that first. So if G98 is active, we're going to rapid to the initial Z plane. What is the initial Z plane? The initial Z plane is the Z we were at before we called the G81, which is Z1 here. And again, this is not showing all the movement correctly, but we'll look at something that will show that. Okay. And then there's this option that for G99, if G99 is active, you would rapid to your R plane, which we already talked about is this number. So on this part, let's just talk about this. Would you rather rapid to the Z plane or the R plane? So the Z plane, the initial Z is a little bit higher. So if we rapid to that point, we're wasting a little bit of time. Not a lot of time, but a little time. So higher is also safer. So there's less risk of a crash. With these numbers we're using, we're probably pretty safe anyways. These aren't that close to the part where we really need to worry that much. But it's good to know. So, and where would this G98 and G99 go? So you could put it on the same line. We could say G98 right there. Or it could be somewhere up in the code up above that we don't even see near here. So G98, let's look again at these. So there's this group 10, G98 and G99. So it's an entirely different G code group. So you can have it on the same line as your G81. Or you could have your G99 there. Either way. Okay, so now let's look at the drilling. So we spot drilled, and kind of the whole point of spot drilling is to give a good entry for your drill to come down more precisely and not have a risk of walking. If the tip flexes a little bit when it hits, that would be force the drill to walk a little bit, and a spot drill like this is much more rigid than your typical twist drill. So if we want to do now drilling, all I'm going to do is copy this, paste it down here, and then just change the things we need to do. So let's assume it's tool 2. And this is a really important thing to catch. When we change a tool number, we also need to change that H number. Okay, so now we're going to do this peck drilling. And I don't have a specified depth, how thick this part is. But let's assume it's deep enough that we want a peck drill. So peck drilling is where you're retracting between each peck to allow some coolant in there and to clear some chips. So peck drill cycle is going to be our G83. And then we can use everything else the same, except now we need to add a Q value in here. So Q is our peck depth. So in most cases, I use 0.1. A lot of times I'll use like half the drill diameter. But for most drills, 0.1 actually kind of just works. That's what I like to use. So another thing about the order of these things, your X, Y, Z, your Q, your R, your F, it actually doesn't matter. So on most machines, let's see, I'm going to move this to the end. You could do that. You could put the Q at the very end. But it is a little more common to have the Q kind of right before or after the R. And it's also alphabetical, Q, R. So now let's plot this whole thing. So all these points are identical to what's above. So I think it's not showing it twice because it's just on top of the other one. But that's what that is. So G83 is going to peck. It's going to fully retract between each peck. So let's just look at this. So it's going to do exactly what G81 does, but step 3 is a little bit different. It's going to peck to depth, and the increment of the peck is this Q value, 0.1. And then between each peck, it's going to wrap it back out to our R plane, and then continue pecking. Okay. And then as far as like G98 and G99 go, everything else is identical. So G81 is what I always have people learn first because all the other can cycles are just a kind of an extension or have a little bit more functionality from G81, but it uses all the same logic. Okay, so now we're going to, let's copy this and paste this below. So let's use tool 3 let's assume tool 3 is our tap. Okay, so now this is going to be a G84 is our tapping. And for now, I'm going to delete this Q. Okay, so when you're tapping, your speed and your feed are super important. All right, so let's talk about speeds and feeds for tapping. So we're going to be using a 1/4-20 tap. So that means it's a 1/4 inch nominal diameter of the threads, and then it's 20 threads per inch. So if you were to measure an inch long, you'd be able to count 20 peaks of this thread, basically. That's what that means. Or if you measure 1/2 inch, which is the easier way to do it, you could count 10, or even a 1/4 inch, you could count 5 because it's a 1/4 of 20. So basically, there's 20 threads in an inch. In machining, we're usually more concerned with the pitch. So the pitch is the distance from one thread to the next. And the way you calculate your pitch is just 1 over your threads per inch. So for a 1/4-20, that's 1 over 20, that's 0.05, which matches this number, 0.05. So your feed rate is going to be your pitch times your RPM. So people always ask, okay, we know what the pitch, we can calculate that. How do I get the RPM? So I usually would just start around 500. It depends on, for a bigger tap, you're probably going to want to go a little bit slower. For a smaller tap, you might want to go a little bit faster. But like for a 1/4-20, somewhere between 200 and 500 works well for that. In most cases, I'd probably use 500. But let's just do this calculation. So let's assume we're using 200 RPM. So 0.05, which is our pitch, times 200 RPMs equals 10 inches per minute. So that's going to be our feed rate on our G84 if we're using spindle speed of 200. And then we can look again down below. If we're using 500, it's going to calculate out to a feed rate of 25. So if we look back at this, our spindle speed's 200, which is what we have. We're going to be using a feed rate of 10. And so the tap will feed all the way to the bottom of this hole. And then it's going to reverse the spindle and feed all the way back out. Here's where there's also something I didn't catch here. We have a Z depth. For our drill, we want to go a little deeper than this. Let's say we go 1.5. So I'll just put in a number 1.25 and then z negative 1. If this was a blind hole, you always want the drill to go deeper than your tap. It doesn't necessarily need to be a 1/4 inch deeper. But if it's a through hole, you want to drill all the way through your part so that you can have plenty of chip clearance. All right, so on newer and more expensive machines, you'll have rigid tapping, which basically means you can put the tap just in a collet in a typical tool holder, and the controller has enough precision control of the spindle versus the z-axis movement to perfectly correlate the z motion with where the spindle is in its rotation. So if you don't have rigid tapping, which might be you're on a less expensive machine or an older machine, you're gonna have to use something like this. This is a floating tap holder. So that tap holder can actually push and pull a little bit to allow some alignment of the z-axis travel with the rotation of the spindle. So you're definitely going to want to know if your machine is capable of rigid tapping. And in general, rigid tapping is better if you have it. Okay, so let's talk about some differences between Fanuc and Haas. So we can look back at our G codes here, and our M codes actually. So there's this M code here, M29, rigid tapping mode on Fanuc. So if we're using a Fanuc and we're doing rigid tapping, then we're going to put an M29 here. And on that line, we're going to put our spindle speed. So typically you want the line immediately before your G84. And it kind of replaces your M3 S200. So you could leave this M3 here or you could leave it off. But M29 is telling the Fanuc controller that we're doing rigid tapping. And it's a spindle speed of 200. Another thing you can do with the modern Fanuc controllers is you can do peck tapping. So I'm going to do 2.25. So basically that means what it's going to do is for every 1/4 inch it taps into the part, it's going to reverse just to break the chips. And then it's going to keep going. And if you are on a Haas, you're actually not going to do this M29. Haas assumes you're wanting to rigid tap to begin with. So on a Haas, you can't do this Q.25 either. But what you do on a Haas, if you do want to peck tap, you're just going to have multiple G84s to different Z depths. And we'll look at that too. All right, so I have some code here that was generated from Fusion Cam software. And this is Fanuc code. So I have some extra stuff in here. So I did a facing pass. This is with a 1/2 inch end mill, so it's having to go back and forth a few times. But from my previous video, you should understand or recognize the G2, G1, G3. Those are all there. So those are allowing that back and forth motion. And then I have a 2D contour that's also very similar to that video, the previous video, where it's just going around the outside of the part and then arcing out at the end with the G3. And then we get to our drilling. So we should recognize this now. We have a G81, and this is starting at x.5, y negative 0.5. This depth is slightly different, but that's okay. And then it just lists off every x, y point. So this one is actually going the way I should have. It's going along x, getting all those first 10 points, and then moving down 1 in y, and then moving negative in x. So that has all the points there. And then we have our G83. And there's our peck depth. We're going deeper with this one. It ends with a G80. That's super important. Got to cancel it at the end. And then here's our G84. So this one, for some reason, it puts in a P. I guess this P usually means a dwell. So I guess in a Fanuc controller, you can do a dwell with your tapping cycle. I usually don't see that P there though. So you can leave that off. But we do have this M29. We're doing S500 with a feed rate of 25. So we calculated that. And then that's the end of the program. So we can compare this to the Haas. It's going to be basically the same. We have our G81, same points, G83, and the same points, and then our G84. All right, so I also wanted to look at this G95. Okay, so here is showing how we can use G95 instead of your typical G94 for tapping. So G95 gives you feed per revolution. So that means on a tap, you're actually just putting in the tapping thread pitch as your feed rate. So G95 means you're using the pitch as your feed rate. This is the Phoenix style with the M29. So the benefit of this is you don't have to calculate your speed and feed precisely. The feed is just the pitch. So you can use any spindle speed and your feed is still going to be this. So this is a Phoenix style, and then here's the Haas style with the G95 is active, and you're using your pitch as your feed rate. So just a little bit different way of doing it. Some people prefer one or the other. There is no right or wrong, but maybe you have a preference. All right, so there's a few other can cycle G codes that I figured were worth mentioning. So we did G81, G83, and G84. For all of those, G80 is what cancels it. Okay, the other ones I want to mention is G82. This is a spot drill can cycle. So it's just like G81, except you can put in a P value to dwell at the bottom. So if you want to dwell at the bottom, you use your G82 instead of your G81. G73, so there's also these G codes in the 70s that are can cycles too. So G73, very similar to G83, but it's not going to be fully retracting between each peck. It's just going to back off just enough to break that chip and then keep going. So the upside of that is it's going to drill a lot faster. The downside is you're not getting coolant to the tooltip between each peck, so you could potentially generate more heat that way. And heat is our enemy in a lot of cases. And then the last one, we did G84. If you're ever using a left-handed tap, it's going to be just like G84, but G74 is going to be your left-hand tapping cycle. All right, so I'm just going to end there. I know there's a ton of stuff in this video, and hard to believe how much work goes into creating these videos. So if you appreciate it, I hope you like and subscribe, and I'll keep these cool videos coming. So thank you for watching.